Greetings, physicists. This video is about how to solve problems that involve center of mass. So, we're starting off with a flagpole. And this is a flagpole that's stuck to a wall at an angle, like this. And put a little dude on the end there. And we are saying that this flagpole is 32 kilos. No, so it's 3.2 kilos, 3.2 kilograms of mass. And they tell us where its center of mass is. It says the center of mass is 1.6 meters from the point where it attaches to the wall. So that's the point where it attaches to the wall. So from there, and I assume that's 1.6 meters along the flagpole. So 1.6 meters there. And we have the angle of the flagpole, which I didn't leave myself a lot of room to draw. We'll just put it here. The theta is 25 degrees. That's going to be this angle here from the horizontal, from there. All right, and we're asking about torque. Well, essentially, what I would do here, so I'm going to draw right there. That's the center of mass of this flagpole. And gravity acts at that point. So a free body diagram at that point would say mg down. And then the torque, in this case, is going to be the radius cross that force, or cross that mg, essentially. Now the cross product means that I can't just use that 1.6 meters because it has to be, essentially, it has to be this perpendicular radius. So to get that perpendicular radius, I'm going to have to draw me a triangle. So this is the 1.6 here, and this is the perpendicular, and that's a theta of 25. And we draw a vertical down here, and we do have a right triangle, so we're looking at, we have a hypotenuse, we need an adjacent, which looks like it's going to be a cosine. So, when I actually plug that into my torque equation, that's going to be torque equal to R cosine theta cross F. Actually, once I've put the cosine in there, I can just times F. Like that. Okay. And we can plug stuff in. R was 1.6 cosine 25 times the force, which in this case was mg, so 3.2 kilos. Sorry, this should be meters. And gravity is 9.8 meters per second squared. So let's put that into our calculator. And what I see is 1.6, 3.2, 9.8 cosine 25 equals 45. And we have a kilogram meter per second squared, which is a Newton, times a meter. So that is 45 Newton meters. And I'm keeping 2 sig figs because that's pretty consistent with what I've got here. All right, 45 Newton meters of torque. Not too bad. All right, let's keep going. A seesaw problem. You can't teach center of mass without having a seesaw. I think there's actually a law that prohibits leaving out seesaws. So we got Emma and Noah playing on the seesaw, got their masses. We know where Noah is sitting. We got to know where Emma's going to sit if we want to balance that seesaw. So let's draw us a seesaw. Here is our seesaw. We will put Noah on the left. There he is. And we know that he is away from that pivot point 1.6 meters. And we know he has a mass of 22 kilos. We will put Emma on the right, because girls are always right. And she has a mass of 25 kilos, but we do not know where she is going to sit other than that she has to balance it. So we know where the center of mass is. The center of mass of these two is right dead, well, maybe not dead between them. I don't think they're going to be equal distances from it. But essentially, they are sitting such that their center of mass is right over the pivot point because the seesaw pushes up here. So that's fine. I prefer to do this problem like a torque problem. So what we'll do is we'll start with Noah's torque. Noah is doing a torque equal to R cross F. And we know his R, his distance from the pivot point, is 1.6. And his F is mg, right? Mg is what's causing that force. So we have times 22 kilos times g. That's going to try and cause the seesaw to go this way. Emma has a torque in the opposite direction. Emma's torque, so this is Noah's torque, Emma's torque will be equal to her position, her distance, which we have no idea. But we know that her mass is 25 kilograms times g. Now you can go ahead and multiply some things, but I'm going to set these two things equal to each other, and we are going to get 1.6 meters, 22 kilograms, 9.8 meter per second squared equal to R, 25 kilograms, 9.8 meter per second squared. Look at that g canceled, which if I had solved this properly, I would have solved first before substituting in and wouldn't have had to copy that over so many times. So I did the long, inefficient way. So what am I doing to get R? I'm taking 1.6 meters, I'm multiplying by 22 kilograms and dividing by 25 kilograms. It should give me R. Kilos will cancel. I'll get meters, which is what I'm looking for. So 1.6 times 22 divided by 25, and I get 1.4 meters. And so if we go back up to the picture, there she is. Her distance is a little less than his. Should make sense, right, to balance because she has slightly more mass than he does. That's how you do that as a torque problem. So let's go forward. This center of mass problem is about calculating where the center of mass is. So we got a gymnast, and you can see my beautiful drawing skills. There's a gymnast, and he is performing on the rings, right? Suspended way up in the air, holding those two little rings, and you can see that is what's considered the pike position, where you keep your chest straight up and you kick your legs straight out like an L. Hard to do. You gym rats will recognize this as a very difficult abdominal exercise. So we also have, I've marked on there are 2 points. There's where his head and his torso and arms, if you were to take the average center of mass, it's right there on his chest. And then if you were to take his legs together, their center of mass right there in the, looks like just left of the knee. And what we want is to calculate the total center of mass of the entire gymnast as one dot. Now, to do this, notice that this has got an x distance and a y distance, so we're going to have to do this in 2 different dimensions. For our purposes, I will solve each of those independently. So I'm going to start with the vertical. Let's do the vertical first. So vertical-wise, we have, and so remember, our center of mass equation is position times mass for the first one, plus position times mass for the second one, all divided by the sum of the masses. And that will give us the position of the center of mass. All right. I know I drew x's there, but this also works for y's. Doesn't matter what direction you're using the equation is the same. So I'm going to plug in. So let's look at the vertical positions first. The 45 is vertically right about here, which is maybe halfway between, is about 50 centimeters, and the 30 is right at about 20 centimeters. So I'm going to plug that in. We have the 50 centimeters times the mass, which was 45, that was for the torso, plus we had the 20 centimeters times the 30 kilograms was for the legs. Those were the vertical points only. Divided by the total mass, well, the total mass together is 45 plus 30, so that's 75 kilograms. And all of that should add up to the position of the center of mass. All right, let's do this. 50 times 45. I'm going to leave this in centimeters. Actually, if you want to convert to meters, go ahead, but I will get an answer in centimeters, which is fine with me. Plus 20 times 30 divided by 75. And I get 38. So my vertical is at like 38 centimeters. There we go. All right, so I'm going to make a little note. That's the y center of mass, so I don't confuse myself later. Now, when I go for the x coordinates, if I look at the chest coordinate, the torso coordinate, that looks right at about 20, and if I look at the legs coordinate, that's right at about 40. So let's plug those in. I'm going to have 20 was the chest coordinate, and the chest is a 45 kilogram chest, plus 40 was the legs coordinate and 30 kilogram legs, divided by a total mass of 75 kilograms. And again, I'm going to leave my stuff in centimeters and get an answer in centimeters. So 20 times 45 plus 40 times 30 and divide that by 75, and I get 28 centimeters, and that is the x center of mass. So I've got these coordinates: 38 in the y direction, 28 in the x direction. Let's go map that. Let's go find that on our drawing here. 38 and 28. 38 in the y direction, which is right about there. And 28, well, if that's 30, which is halfway, the 28 is going to be slightly below that. So the center of mass of this guy is probably, and I may have drawn this a little off, but it's probably right about where his stomach is, which is true of most guys. Guys tend to have a center of mass closer to their stomachs, and girls, I think, tend to have their centers of mass closer to their hips. Either that or have it backwards. He is bent in a weird shape, so that does change things a bit. If his legs were straight up and down, it would lower his center of mass a little bit more. All right, that's how you do it. Center of mass. Hope this was helpful to you.